Hello everyone and welcome. In this video sponsored by Skillshare, which we will get into more at the end of the video, we are talking about GM's patented variable compression engine with independent compression and expansion ratios. What? Now this all probably looks like a big mess of information, but I promise we have a nice logical flow here and we will eventually understand how this engine works by the end of the video. The big idea here, GM doesn't want to compromise between power and efficiency. They want both. Just like every other car maker out there, they both want power and efficiency. They don't want to sacrifice one or the other. And so this is one solution which GM has come up with. This patent dates November of 2018. Now, GM's engine has independent compression and expansion ratios. So the first thing we need to understand is what's the difference. So a typical engine will have your 4 strokes: intake, compression, power, exhaust. And so here we've got that laid out and we're going to illustrate what the difference is between a compression ratio and an expansion ratio. So on that intake, your piston moves down to the bottom. Once it's at the very bottom, the volume within that cylinder divided by the volume once that piston goes all the way up to the very top dead center, V1 divided by V2, that will give you your compression ratio. So it's the volume of air with the piston at the very bottom versus the volume of air with the piston at the very top after that compression stroke. Now your expansion stroke is then the volume after that piston goes down from the power stroke. So at the very bottom of its stroke, that volume divided by the volume when it's at the top of its compression stroke. And so as you can see in the typical engine, these are going to be the exact same. V1 is equal to V3. So the compression ratio and the expansion ratio are exactly the same. Well, this leads us to a problem. So if you look inside your cylinder, if you've just had that spark ignite, you have the power stroke occur, it pushes down this piston. Once this piston reaches the very bottom, there's still a very high amount of pressure within this cylinder. And then you open your exhaust valve and all that high pressure escapes out your exhaust. That's just wasted energy. Whereas if you could use that pressure to continue to push this piston downward, if it were able to go down further, then you could get more useful work out of that pressure that's built within that combustion chamber as a result of burning that air and fuel. So that means you could get more work. That means you could have better efficiency. So you use the same amount of fuel to go a further distance. That would be ideal. So engineers are very clever and they came up with a solution in order to have a greater expansion ratio versus the compression ratio, and this is called the modern Atkinson cycle. And so essentially what they're doing here is decreasing the compression ratio. And so as that piston pulls in the air, it then continues to push up and presses out some of that air without the intake valve yet closing. So the piston has already started its compression stroke and your intake valve remains open. So by using valve timing, they're decreasing the compression ratio because some of that air and fuel is pushed back out. And so by doing so, now you can see your compression ratio is going to be this volume right here, but that piston gets to move all the way down to here, and so your expansion ratio is greater. And so by doing this, that pressure pushes down on that piston for a longer amount of time, and you're able to get more useful work out of it, so it's more efficient. The challenge, of course, here is, as you might notice, if you're pushing out some of that air and fuel, if you have less oxygen overall to burn, then you're not going to make as much power. And so that's the challenge. While you make power more efficiently, you don't make as much of it. So great for an engine that's looking for high MPG, but not so great for an engine that's trying to get you, up and cruising up to 60 miles per hour up on the highway real quickly. So remember, GM's engine wants 2 things. They want independent expansion and compression ratios for efficiency, and then they want a variable compression ratio for power. And so how do they do this? Well, in order to understand the independent expansion ratio and compression ratio portion of it, we need to understand a traditional Atkinson cycle engine. And this probably looks fairly complicated. It's not. It's actually pretty simple how this engine works, and we're going to get through it. So, just looking at it on the surface here very briefly, we have the end of our intake stroke, the end of our compression stroke, the end of our power stroke, and the end of our exhaust stroke. And there's really just 2 main differences between this traditional style Atkinson cycle engine and the engine that you are used to seeing in your car. So the first one being is that in our cars, we're used to this engine going up and down, and the bottom, that crankshaft, just going in a circular motion like so. So it just goes up and down, and this goes in a circle. And we have 2 rotations of the crankshaft. That's what I've drawn here in red. So that purple point is fixed. This purple point is fixed. Those 2 points never move. Everything else moves. So that purple is fixed, and this red crankshaft just rotates in a clock right here. Now the difference being is that it only rotates once for all 4 strokes. So one of the biggest differences is that the crankshaft only rotates once for all 4 strokes. The second difference being the piston, instead of doing this up and down circular motion, it's just going like this. It's just bouncing back and forth. So the piston itself is just doing that. And in one rotation of this crankshaft, this piston goes over to here, back over to there, back over to here, back over to there. And every time it's in the center there, it pushes up and then it comes back over. And so looking at this right here, here's our piston, here's our connecting rod, very similar to what we have in a traditional engine. Then you have this crankshaft here, which rotates about that fixed purple point over here with another link, and you have this center link right here connecting that crankshaft to that connecting rod. So that center link, all it's doing is, as this red crankshaft rotates around, you can see those 90-degree rotations there. As it rotates around, this center link just pushes back and forth like so. That's all it's doing. So this is rotating in a circle. That center link is just kind of going back and forth like this. And by going back and forth, it's pushing that piston up each time. So you can see here, it's going to rotate 90 degrees. It's going to start to push that piston up. Then you're going to have it continue to rotate another 90 degrees, your crankshaft. It comes back down as that connecting rod is now all the way on this side. Then it continues to rotate down. So as it rotates down, it pulls that center link over. That pushes this back up. And so you just repeat that with this piston going back and forth like so, up and down with the connecting rod going back and forth, rather than a circular motion like you see in a traditional Otto cycle engine. And what this does, based on the geometry of where you have these fixed points and that crankshaft, is it actually varies your compression ratio from your expansion ratio. So you can see that here. As it comes over, it pushes it up this distance, but it's only come down for the intake stroke to this line right here. And then for the power stroke, it goes down an additional distance. So your expansion ratio is greater than your intake ratio. Remember, the only 2 differences being, we have this crankshaft in one rotation, this piston will go, the connecting rod will go back and forth, and that will cause this to go up and down twice. So very simple system. It just uses this system of linkages in order to make that occur. It looks far more complicated than an Otto cycle, but in principle how it works is actually fairly simple. And so if you're to trace the position of that piston, you can see it comes down for the intake stroke, back up for the compression stroke, goes further down than it did for the intake stroke for your expansion stroke, and then back up to the beginning of your intake stroke. And so you have that independent intake stroke distance versus your power stroke distance, which allows for greater efficiency. Okay, so now we can get into the meat of GM's patent. And so they have 2 different modes. They want to operate efficiently, or they want to operate in power mode. And so how do they do it? Well, if we go back to our traditional Otto cycle here, remember we have these 2 fixed points, the center of your crankshaft right there in purple, and then this pin right here, which just allows for this back and forth motion that piston's undergoing. So remember that bottom pin right here, so this little point is just going to rotate like so in order to allow that piston to go up and down. And so what if we were to change where this fixed point was? What if we could actually anchor this in a different location? Well, if we were to do so, we would alter the compression ratio. We actually would be just shifting this curve here how we wanted to. And so that's where GM's patent comes in. So they have this traditional Otto cycle style engine here. And then this point right here, instead of being completely fixed, it's on this worm gear right here. So you can use an electric motor, you've got a worm gear, and you can rotate this gear. And so that means you're changing this purple position right here. You're pulling it this direction. And so by pulling that this direction, as you can see, the crankshaft has remained in the exact same position, but we've rotated where this fixed position is, and in doing so, we've decreased our compression ratio. So very clever little solution here in order to have this have different compression ratios depending on what you're going for. So a higher compression ratio would be used for efficiency. The reason you can't use a really high compression ratio for power is that you start to run into issues with knock. So you have to limit your ignition timing, meaning you're firing that spark plug very late, and in doing so you don't make much power. So in order to make more power, you want to be able to decrease the compression ratio. And so that's what they're doing here by changing this position of that fixed point. They're decreasing the compression ratio. Then likely the case would be you would add forced induction, and with additional forced induction, whether it's a turbocharger, supercharger, and that lower compression ratio, you don't have to worry about knock because you've decreased that compression ratio. And then you can make more power because of it. And so it's a clever solution where you have, instead of kind of the modern style Atkinson cycle, you have actually a traditional style Atkinson engine, but with this modern twist on it where you have a variable compression ratio. So fairly neat. And what this is doing is just shifting this curve right here in your favor. So if you want more efficiency, you increase that compression ratio. If you want more power, you decrease it, and you probably would add some boost in order to increase power. So a very clever system, and ultimately based on something very simple. And again, when you're looking at a patent, don't just assume that this is exactly what it's going to look like. Patents are kind of going to be the simplified version. They will probably have a different system of linkages and how it would actually be put into production if it ever is put into production, rather than looking exactly like this. But this gives the general idea of how that engine style would actually work. Now again, a big thank you to Skillshare for sponsoring this video. There's a link in the video description, and the first 500 of you to sign up using this link will get 2 free months of membership. Now obviously I spend a lot of my own time learning and teaching. That's what this channel is all about. But I also spend a ton of my time creating, and that's really where Skillshare as a platform shines. It's an online learning community designed for creators, whether you're just about to start out or well into your career. Whether it's photography, video editing, script writing, animating, or even the more business-oriented side of being a creator. And they have thousands of classes to help you learn new skills and apply them in the real world. Again, you can sign up using the link in the video description, and the first 500 will get 2 months free. If you have any questions or comments, of course, feel free to leave those below. Thank you so much for watching.